All right, everyone, our third speaker of this morning's session is going to be Alessandra Buonanno, talking about accurate gravitational wave astronomy. Thank you, Alessandra.
First of all, thank you very much to the organizers for inviting me to this very inspiring conference. Unfortunately, I didn't have the honor or the privilege to meet Steven Weinberg in person. I wanted just to mention here one paper by him. I think for what I know is the only paper he wrote interfacing gravitational waves. Was a paper written in 2003. At the time, I was still working in part in cosmology of the early universe. And he pointed out that anisotropic stress tensors can be due to the free streaming neutrinos could affect actually the stochastic background of gravitational waves for modes that re-enter the Hubble radius at a time in which the universe is dominated by radiation. The effect is of the order of 10%. And I found this quite amazing, considering that he was 70 years old at the time, and is one of the most cited papers of the last 20 years of his career. Okay, let me start with my talk now. I'm pretty sure that everybody in this room has seen this plot. It represents a summary of the coalescence of binary black holes and neutron star binaries and neutron star black hole binaries discovered by LIGO and Virgo since the first event 9 years ago. You can see here the first event on the left, 150914, the first binary neutron stars that was mentioned by Brian before. The largest binary black hole observed with a total mass for the final object of 150 solar masses. The most asymmetric event discovered the 14th of August 2019 with a mass ratio around 10. And finally, I wanted to highlight an event of the ongoing run. The paper was published just this April. Was a neutron star black hole with the black hole squarely in the so-called low mass gap between 3 and 5 solar masses in the region in which we don't find black holes in our galaxy. So in this brief presentation, I will describe the role that waveform models have played and continue to play for detecting the signals to infer the properties of the sources, some recent theoretical advances, and then I will discuss the problem of addressing the challenging accuracy that we have to achieve with future observations and also of new facilities on the ground and in space. So this is a timeline of the detectors over time. As I said, we are at the fourth run. The numbers here represent the range at which the detector can see observed binary neutron stars. And so the increase of this number means the detectors are becoming more and more sensitive. The fourth run started in May of last year. And so far, 156 candidate signals have been observed. You may know about them through the public alerts, plus just the event that I mentioned before. The run will end in June of next year, so we expect many more detections. Then there will be a period of still upgrade of the interferometers until the last run of this decade will start 05 at the end of 2027. At the end of this decade, or perhaps the beginning of next one, we expect LIGO India. And then there will be further upgrades in early 2030 that go under the name of A-Sharp and Virgo Next. And I'm sure Gabriela Gonzalez this afternoon will tell you more about the development of the instruments. At least for this decade, these detectors are going to see sources, let's say, in our local universe with a redshift between 1 and 2. So we are interested, or I'm particularly interested in predicting the signals, the shape of them, because the waves are like fingerprints of the source. The properties of the sources are imprinted in the waveforms. For example, from the frequency evolution, we can infer the masses of the source. From the amplitude, the masses, we can infer the distance where the source was located with respect to the Earth. From the time of arrival, the phase and the amplitude at the different detectors, for example, the two LIGOs and Virgo, we can infer the sky location. This particular waveform I'm showing you here is for a quasi-circular orbit, black hole, two black holes, and with spins of the black hole align along the direction of the angular momentum. And what you see here is the case in which the orbit is eccentric, or the spins are, on the other hand, precessing along the direction of the total angular momentum of the system. There are differences between a waveform of two black holes and two neutron stars, because the neutron stars has a parameter which is 0 for black holes, which is called the tidal deformability parameter, which create dephasing differences even before reaching the merger. And by measuring this parameter, we can learn about the composition of the neutron star. Finally, if we match the data with the templates that are built in an alternative theory of gravity, we can learn which one is the theory in the strong field, high dynamical regime. And until now, general relativity has passed all the tests, as you will see in a moment. So to produce waveform, we have to solve what we call the two-body problem in general relativity. This is complicated by the fact that the Einstein equations are nonlinear. And we have two main tools to tackle the problem. One is numerical relativity. Soltiokovsky talked a bit about that yesterday. This is the best tool at our disposal, produce the most accurate waveforms, but because it's time consuming to produce the simulations, it's limited in a certain region of the parameter space, mass ratio, and also length of the simulations. We have then to resort to analytical methods. So these are approximate solutions of the Einstein equations. The oldest one is post-Newtonian theory that expand the Einstein equations in powers of V over C, and also Gm over RC square. R is the separation between the two bodies. The two are intertwined because of the viral theorem. And this is valid in the region in which the black holes are very far from each other and the velocity is still quite small. In the last 5 years, has become very popular, actually, this post-Minkowskian expansion of the Einstein equation in powers of G over R. It's a weak field, but it's not restricted to low velocities. So it's a kind of resummation of the post-Newtonian expansion in the velocity, and is particularly interesting for bodies in fast motion. Now, if the binary has two objects which have very different masses, then one can expand the Einstein equation in the mass ratio, and this goes under the name of gravitational self-force theory. It is particularly important for the so-called extreme mass ratio in spirals that are targeted sources for the LISA detector in space. Then we can put these approaches in a framework which is called the effective one-body theory that can resum them, make them more accurate toward merger. And the effective one-body approach also provides approximate answers for the merger, and then the ring down, and can be made more accurate using numerical relativity results. We can also build waveform in frequency domain in closed form. They are less accurate than the effective one-body ones, because you have to do some assumption to make them in closed form, but they are very, very efficient, very fast to generate, and they are built by combining together effective one-body, post-Newtonian theory, and numerical relativity. And you can see here, in fact, the amplitude in frequency domain and the derivative of the phase in frequency domain as a function of frequency, and you can appreciate the simplicity or the smoothness of this function, and which allows actually them to fit not in a very complicated way. Now, until now, the majority, actually almost all the waveforms that are used for the analysis are produced in vacuum. Of course, in the case of neutron star, we have also to take into account the matter, the neutron star. But in the last few years, it has become quite interesting to include effects that could be due to the environment. For example, in the case of extreme mass ratio in spirals, the small body, the small black hole, could be in an accretion disk around a massive black hole. And the effect of the disk can have an impact, the disk can have an impact, the gas, on the spiral of the small body. Or even the binary system could be, in some case, in AGNs. The black holes can move in medium, creating also some effects. And also one can go beyond actually general relativity in the sense build waveform in alternative theories. And from the point of view of doing perturbative calculation, this means that you will need to include new operators when building your Feynman diagrams, for example, scalar fields, vector fields, etc. Also take into account the environment in that way. Okay, so I have just one slide to tell you a little bit more how these waveforms are calibrated using numerical relativity. So in the plot here on the left, you have an example. You start, for example, in the case of the effective one body with a waveform which also include mergering down here in blue in the upper panel. You compare with numerical relativity simulation. You see that there is some dephasing that accumulates because the numerical relativity waveform is more accurate. And then you basically include the information from numerical relativity until you get a very good agreement in the model, for the model. Then you repeat this for many numerical relativity simulation at your disposal, which in the case of the most recent waveform models that have been developed for the ongoing run, one used of the order of 400 numerical relativity waveform, mainly from the SXX collaboration. You see here the spread of the waveform in the mass ratio with different colors depending on the mass ratio and the binary effective spin. At very low mass ratio, we use waveform produced with the so-called Tchaikovsky actually code. And then once you do the calibration in each point of the parameter space where you have numerical relativity waveform, you then extrapolate the model everywhere else. So besides waveform produced with the SOBNR family, there are, as I mentioned, the inspire mergering down phenomenological one. There is another family from the EOB formalism. And then there are numerical relativity surrogate waveforms. This is very important. These are waveforms that are produced interpolating directly numerical relativity waveform where they are available. And of course, they are not available everywhere in the parameter space, and they are restricted also to the length of the numerical simulations. So then the waveforms are used to produce the template bank that are used for the search, the match filtering search. This is a projection of the template bank in the mass plane M1 and 2. So for low masses, one uses plain post-Newtonian templates, and for neutron star black holes and black holes where we need also the merger, effective one-body waveforms are used. So I want to give you an example where this waveform played a certain role. This is the event called the 1908-14 that I mentioned at the beginning. It goes under the name of a binary with a puzzling companion because the primary mass is certainly a black hole having a mass of 23 solar masses, but the secondary mass has a mass too large to be the one of a neutron star and perhaps too small to be the one of a black hole formed from a collapse of a star. So we don't know actually. But the peculiarity of this event is actually the mass ratio, which is around 10. And the more substructure you have and more asymmetry you have, in complexity you have in your binary due to the different mass ratio spins, the richer is the spectrum. So you don't produce just the dominant quadrupole radiation, but also the subdominants, the higher harmonics. So this is the total radiation from this event just in the last seconds of the evolution, decomposed then in harmonics. These harmonics become more and more important toward merger. Now, more quantitatively, if you compute, in fact, the posterior distribution associated to the secondary mass, only when you include the presence of these harmonics and also the precession of the spins, which are denoted here by a P and the HM, you can get actually tighter posterior distribution and determine the mass of the secondary with an accuracy of 10%, so that, this could raise this problem of the puzzle, that the mass is actually quite ambiguous for this event. I wanted also to mention the neutron star black hole that was just published in this April. This is a simulation that represents the event where the neutron star is swallowed by the black hole at the end, leaving almost no accretion disk around. These are the results of using the waveform model to recover the masses of the object. In particular, this 230529 is represented by this line here. To deduce that the secondary is a mass, the only way this was possible for this event is the recovery of the mass, because the tidal deformability parameter that would be a smoking gun for a neutron star was not actually measurable due to the low signal-to-noise ratio of the event. And this plot also contrasts this latest event with the binary neutron star 170817, the other binary neutron star discovered by LIGO in Virgo, and also a few binary neutron star black holes discovered during the third run. And Aaron Zimmerman, I'm sure, will give tomorrow more details about the science of during the first three observing runs. The last example I wanted to make about the use of the waveform models is for tests of general relativity. Just one example. So if you are in the frequency domain, you can actually decompose the waveform in an amplitude and in the phase. The phase can be expanded in the velocity in a post-Newtonian approximation. And this is what is written in this formula here. Sorry, this is n equal to 2. And you can see the expansion in V with coefficients in red that are prediction from general relativity. And these predictions are, coefficients that depends on physical effects, spin orbit effects, spin effects, tail effects, absorption of the black holes through the gravitational waves, etc. Now, you can do a test in which you add to this coefficient deviations and deviation, due to some alternative theory, and you can do your Bayesian analysis now using these extra parameters. You then compute posterior distribution for these parameters, and if they encompass 0, you can conclude that general relativity is not violated. And this is the case. There was no violation of general relativity, so you can turn it in a bound on this parameter. And this is what is shown in this plot for the different post-Newtonian parameters, the current bounds. I want to focus on the minus 1 pn correction, which would be a dipole emission. As you know, there is no dipole emission gravitational waves in general relativity. And the best bound was obtained with a binary neutron star, GW 170817, due to the very long in spiral, 3000 cycles. But the next bound is actually set by this neutron star black hole that was discovered in the last year. And the interest of this event is that now it contains also a black hole, which means that it would test theories alternative to general relativity, for which black holes can have hair. Now, in gray, you see basically all the events that were analyzed by the LIGO in Virgo collaboration, and the combined bound obtained either with these effective one-body templates or the phenomenological ones. Okay, so now let me switch to telling you something about the accuracy of these models. So one way of assessing the accuracy is to compute the so-called mismatch. So you take a model, numerical relativity, you compute the overlap, and you weight the overlap with the noise spectral density of the detector. And what you need to know here is just that you want to have this mismatch to be as much as possible close to 0. So the two main waveform models were actually validated against numerical relativity waveforms. In this example, the largest number that we have at our disposal from the SXX collaboration, 1,543. And these are basically posterior distributions for the maximum mismatch obtained varying the mass of the binary. And where are these numerical relativity waveforms for which we validate the models? So the majority of the precessing waveforms have a mass ratio up to 4 and the spin going up to some 0.8. The blue here are the aligned spin model that were used to calibrate these waveform models. So the precessing waveforms from numerical relativity were not used for calibration. So it's a nice way of validating them. But I wanted to give you now an idea, what does it mean that the mismatch is, for example, 10% with respect to 2%. So let me give you an example. You can use a numerical relativity waveform as a signal, and you try to recover with these two waveform models having different mismatch. And this is the result for the recovery of the masses. The waveform which has 12% of mismatch would recover not correctly the mass of the primary. At 90% will be away from the true value. But more importantly, the recovery of the spin is not very good for the model which has 12% of mismatch with numerical relativity, because the parameter that describe precession, which is chi p, will be away from the true value at 90%. And while the binary was highly precessing, this model would say that actually the binary was mildly precessing. And this is not very good because it will affect basically the way in which we can learn about the formation scenario of the binary. One of the ways of learning it is the precession actually of the spins. We expect a binary in globular cluster to have precessing spins, while the one that come from fields to have mainly aligned spins. Now, besides improving models for the quasi-circular case, the frontier is really to include eccentricity. This is a simulation showing the flux of radiation from an eccentric binary where the spin of the primary compact object is also precessing. In the bottom, you see actually the waveform with all these features now that are due to the burst of radiation when the two bodies reach the minimum distance, so the kind of periastron. And so where we are with this modeling of eccentricity. So the waveform models for the first time now include actually eccentricity for spin aligned with the orbital angular momentum in the UB families. I'm showing you the results here, showing the match with the numerical relativity waveform for mass ratio 3 and eccentricity 0.3. You see the different modes that have been modeled. In terms of mismatch, comparing with numerical relativity waveforms, the mismatch can be as large as 1%. So this is not very bad for the first, accurate model at our disposal. And these are the results only including the Tutu mode and for the higher harmonics. The number of numerical relativity waveforms with eccentricity is not as large as for the one for quasi-circular orbits. So this test was done using of the order of 100 XXX NR eccentric waveforms. And we are also eager to actually compare now this model with other catalogs that have been produced for eccentric waveforms. There is more work done in the literature, as you can see here. There have been also results in the literature where people have started to use this eccentric model to analyze the population of LVK, and in some cases obtaining also results that are not consistent with each other, depending on the accuracy of the waveform model that have been used. So more work is actually needed. So let me now spend the last, I think, more or less 8 minutes describing more the future. So we expect new facilities on the ground, the Einstein telescope in Europe and Cosmic Explorer in the US. So these interferometers will increase the sensitivity by 1 or 2 orders of magnitude, depending on the frequency. You can see here the comparison with advanced LIGO, and they will allow to reach actually binaries that are at large redshift at the epoch where the first stars formed. And also, because the sensitivity is going to improve at low frequency, we will be able to see larger black holes than what we can see today with LIGO and Virgo, up to 1,000 solar masses. It's quite overwhelming to think about the number of events that we are going to have in 1 year, of the order of 10,000 binary black holes with a large signal-to-noise ratio larger than 100. Please remember that the signal-to-noise ratio of the events we are seeing with LIGO and Virgo is 10, sometimes 20, and also of the order of 400 binary neutron stars with a large signal-to-noise ratio. LISA, the interferometer in space, has been now adopted by ESA with large participation by NASA just in January of this year. The launch is expected for 2035, so more or less 10 years. This is a beautiful experiment that will open a new frequency band in the millihertz and is going to see complementary sources with respect to ground-based detectors. This is the noise spectral density of LISA, and marked here are the sweep of massive binary black holes of million or tens of million solar masses that we are going to see for months or even an entire year sweeping in band. These are the tracks of the higher harmonics of extreme mass ratio in spirals. And the data analysis of this detector is going to be much more complicated due to the fact that many signals are going to be there all the time and are going to be also very loud. So I'm not going to discuss actually the challenge actually in data analysis, but people have started to do a lot of work on it. Now, I wanted to tell you about the accuracy of the waveform, because this is also very important that we have to improve. I'm going to make two examples, science cases. So let's consider a binary system like Gravitational-Wave 190814, but with a mass not as large, mass ratio 10, but 6, highly precessing. And now let's try to recover. We inject one of the signals being one of the waveform, the state of the art today, and recover with the other one. The signal is too long to do an injection with a numerical relativity simulation. Let's consider the science case of cosmology. As you know, gravitational waves allow to compute the distance to the source. And if we can localize very well the source, the galaxies close to the event, we can get the flow velocity and then the Hubble-Lemaire parameter. So this test is actually not very good, because it tells you that if you use one waveform to inject and the other waveform to actually extract the signal, you find a bias in the distance at 90%. And more than the bias in the distance, you also don't actually localize the source in the sky at 90% credible interval for all the cases, the next observing RAN, a SHARP, and Einstein telescope or Cosmic Explorer. So we need to improve our waveform models, otherwise we will certainly not help in the solution of the Hubble tension. So the other example I wanted to make is spectroscopy. Yesterday we heard from the talk of Sol Teokowski about studying the ring-down phase to extract information on the quasi-normal mode. I want to make an example for LISA, for a moderate mass ratio and aligned spins. So in this case, a signal is injected with a numerical relativity waveform and recover with a state-of-the-art effective one-body waveform. In the model, we add a deviation parameter on the frequency and decay time of the quasi-normal modes. And the test is failing because instead of giving us a posterior distribution that encompasses 0, where is general relativity, because we injected a numerical relativity waveform in GR, we actually get a bias. So we will get a fake deviation from GR. So how to improve this, how actually we address this accuracy challenge? So first of all, we can actually improve our calibration to numerical relativity, because when we do the calibration and we, as I was explaining before, we basically match a numerical relativity and we get the best value, and then we interpolate the best values for different numerical relativity waveform. We actually somewhat don't take into account the fact that in the calibration, we have access to the entire posterior distribution, so we can give a thickness to our waveform, not just taking the best value, but the fact that we have an uncertainty inherent that is present due to the calibration. And so when we do the parameter estimation analysis, we should take into account this uncertainty. So for example, in this example, we inject a numerical relativity waveform again, and we try to recover the model with just using the best fit values, and we have a bias. This had actually signal to noise ratio of 100 405, so it's quite a loud event. But including this uncertainty in the calibration and marginalizing on it, we can actually move the posterior toward the true value, although we get a posterior distribution which is a bit broader. However, this inclusion of the uncertainty is not the whole story. So in order to improve the waveform and address the accuracy challenge, we have actually to build a much more accurate waveform by, as has been shown in several papers right now, we have basically to make the waveform 2 orders of magnitude better than what we have today. And we also have to improve the numerical relativity waveforms, both for binary black holes and the one with matter. And we have actually to include all possible physical effects. I was talking about eccentric binaries, memory, the fact that the bodies, the binary system can be in accretion disk, can be influenced by the presence of a third bodies, because the detector will be so sensitive that all this effect needs to be taken into account if we want to avoid the wrong scientific conclusions. And I want also to mention gravitational lensing, in fact. So in this figure here, you see an example where you have a binary that can be observed by LISA, and the gravitational wave goes through an object, can be a galaxy, can be actually a massive black hole. And depending on the mass of the lens, the gravitational wave will be distorted. The original one is in black, and the color one will be the effect of having the lens, including actually having kind of echoes that are similar to the multiple images that you have in gravitational wave astronomy. In the case of gravitational waves, you have basically several events happening, but coming from the same source. Okay, so in order to address this problem, we have to push the perturbative calculation at higher orders. We have to combine them in a more effective way in the effective one-body formalism. We have to improve the way in which we do calibration. And I want to mention here that, in particular for the post-Minkowskian results, there have been a lot of new results in the last few years, thanks to a new community that has decided to help us, coming from high energy physics and using methods that have been developed, in particular in quantum field theory, computing integrals at higher orders that have been very much used in collider physics. Post-Newtonian calculation have been also improved in the last few years. The frontier is to go to basically 5 post-Newtonian order, which is represented in this plot along the diagonal, because post-Newtonian calculation mix the expansion in G and in the velocity. Post-Minkowskian theory means an expansion in G, and we have to go up to 6 p.m. And we also expect that post-Minkowskian approximation methods can help us in the eccentric case, because they don't expand in the velocity, as I was mentioning earlier on in my talk. So I want to mention here that these results need also to be resummed in the effective one-body framework. And I want to give you here an example of how this happens. This is the binding energy of a numerical relativity simulation extracted for an equal mass system as a function of the frequency. If you were using the perturbative result from PM at 1, 2, 3 p.m., 4 p.m., you have a certain disagreement with an R. If you include them in the effective one-body formalism, you can see how better agreement you can obtain with numerical relativity. And many results have also been obtained just in the last year, including this post-Minkowskian calculation to build waveforms. Lastly, I wanted to mention that another important development that has to happen in the next years concern the MRIs, the extreme mass ratio in spirals, where we have actually to get results at second order in gravitational self-force in the mass ratio. And I want to show you some recent results here. This is a comparison of the second gravitational self-force results for quasi-circular orbit non-spinning for a mass ratio 10, the good agreement with numerical relativity in a regime in which this expansion may not work so well because it's tuning extreme mass ratio in spirals where the mass ratio is 10 to the 5, 10 to the 6. So the fact that works quite well at mass ratio 10 is actually quite promising. So let me skip this slide here and I go to the conclusions. So I want just to say that solving the relativistic two-body problem has been complicated, but certainly has been successful for today accuracy of the gravitational wave observations. And this happened thanks also to the synergistic work between analytic and numerical relativity. So we have to do a lot in the future to obtain this leap of 2 orders of magnitude of improvement if we want to take advantage of the scientific potential of the next runs of current facilities, but also upgrades facilities and the Einstein Telescope, Cosmic Explorer, and LISA. This is just to impress you on the cumulative detections that we will have in the future, in the next decades. And finally, I want to say that I'm very happy we were just awarded an ERC Synergy Grant with Enrico Barausse, Zvi Bern, and Martin van der Mint to actually address the accuracy challenge. And I hope we will make progress in the next 6 years with our groups. Let me thank my department and the agencies and the different collaborations for which I showed results. Thank you for your attention.
Great talk. To what extent do you think machine learning can be helpful for interpreting waveforms now and in the future?
Yeah, thank you for the question. In fact, I had a slide.
Of course you did.
So of course, also in gravitational wave observation, people have started to use machine learning. So we developed actually with the Max Planck Institute for Intelligent System a code which is called Dingo, which allows actually very quick inference. For example, the recent results, this is recent results of this code which is called Dingo, which will be able to basically do inference of a binary neutron star, even for cosmic explorer and Einstein telescope in just 1 second. And this is great considering that today, doing this analysis can take several days, a week, or even more. And for binary black holes, this code Dingo has been reviewed actually by the collaboration and has started to be used. And we are not the only one, actually. I also cited here some papers, including people here at UT, actually, Austin. So very much people are looking into this, are using actually already this machine learning.
I have a question, which is, do we have a mechanism to generate eccentricities that is big enough? We usually think that everything circularizes early on and it'll be mostly circular in spirals, but how do we generate big eccentricities?
Okay, so in fact, one of the reasons why until now the waveform modeling has focused mainly on quasi-circular waveforms is because we expect, for binaries in field, so-called isolated binary that originally you had to start in the binary and then they went through collapse, etc., and form black holes or neutron star. So the eccentricity would be washed out. But there are subpopulations, and we expect to be of the order of few percent of the number of events that we have observed until now, so few percent of the entire population that could come from, for example, globular clusters where you have very dense, environment, and there the binary form from dynamical capture. And in this case, there is not a lot of time then to circularize. And so that's one way, you expect them to be eccentric. The presence of a third body, a way, not so close to the binary, but still close enough to have an impact, can also tend to create eccentricity. The Kozai mechanism is called. So these are mechanisms. As I said, we expect that maybe with 100, 200 of events, a few percent could be, maybe 1 or 2 could be eccentric. And that's why now there is a lot of interest in that. But I want also to add that for massive black holes, 10 million solar masses, the source for LISA, that's a different story. People expect the eccentricity to be actually quite large, even 0.8, 0.9. So for that, the inclusion of eccentricity is important.
All right. Thank you very much, Alessandra, and everybody at this session. We meet back here at 11:15.